Hello, my dear friends. I'm Shubham from LearnoHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So friends, as you all know, we are studying your ICSE Chemistry chapter number 3, study of acids, bases and salts. And till this video, we have completed the classification of acids, its definition, classification of bases, its definition, classification of salts, and its definition. Now, in this video, we are going to cover up the properties of acids and bases and the pH scale, introduction to pH, and we are also going to see how we can test a particular solution and tell that whether the particular solution is acidic or basic or neutral. Okay, so if you have missed the previous two videos, please do watch, because those are the basics of acids, bases and salts. Otherwise, you won't understand what we are learning today in this video. Okay, so without wasting much time, let's start and let's rock. So first, starting with the properties of acids, and we are going to see first the physical properties. Okay, now in physical properties, first is the taste of acids. Okay, what taste acids actually have? They are sour in taste. Okay, but hearing that they are sour in taste, don't just go and taste acids, because it is very dangerous to do so. Okay, because the acids are corrosive in nature. Okay, they can cause painful burns and blisters. So please don't do this. Okay, disclaimer. Next, physical state, they exist in solids and liquid state. Okay, so there are some acids which exist in solid state. They are oxalic acid, phosphoric acid. We actually know their formulas as well. And those acids which are existing in liquid state are acetic acid, formic acid, carbonic acid. Okay, all these are weak acids, we already know. Then hydrochloric acid, nitric acid, these are strong acids, right? And then sulfurous acid, again it's a weak acid. Okay, and sulfuric acid, again strong acid. So you can either remember in this way: weak acid, strong acid, weak acid, strong acid. So 3 weak acids you remember in one go. Again, then 2 strong acids, hydrochloric acid HCl and nitric acid HNO3, and then again a weak acid and strong acid. I have deliberately paired up the sulfurous acid and sulfuric acid, okay, so that you would remember easily. Sulfurous and sulfuric, H2SO3 and H2SO4, okay, they are together. So all these acids are existing in liquid state. But an interesting thing, now all these acids except sulfuric acid, if we keep these acids at room temperature or if we heat them, okay, so these acids, they vaporize. Okay, so what does this mean? They are vaporizing easily. Vaporization means they are getting converted from their liquid state to gaseous state. Okay, so this is what is called as vaporization. So all these acids except sulfuric acid are volatile acids. Okay, volatile acids means they vaporize easily. And what does this mean? What does this mean? Vaporizing easily means if we keep the particular substance at room temperature, it gets converted into, from liquid state, it gets converted into gaseous state. Or if we heat that substance around 100 degrees centigrade, okay, till 100 degrees centigrade, so at that temperature also it gets vaporized. So if substance is behaving like this, then we are saying that okay, the substance is vaporizing easily, and it is vaporizing easily means it is a volatile substance. So these acids also vaporize easily, so therefore they are volatile acids, while sulfuric acid doesn't vaporize easily. It doesn't get converted into its vapors, okay, from liquid state, it doesn't get converted into gaseous state easily. That's why it's a non-volatile acid. Okay, next is effect on skin. So if strong acids get dropped on your skin, so it may cause very much pain. Okay, it may cause painful burns as well as blisters. But if weak acid, okay, by accident it falls on your skin, so they are non-corrosive. Okay, no need to worry about them. Like acetic acid, vinegar. Okay, if you have vinegar in your home, if it falls on your skin, so you would know that it doesn't cause any burn or blister. But don't try it. Okay, no need to try all those things. It doesn't cause any harm in very small quantity, but in large quantities it may cause harm. Okay, next, acids conduct electricity in aqueous state. So this is the last physical property. Now actually we have studied this. Okay, do you remember we have studied in chemical bonding, in covalent bonding, okay, the polar covalent compounds in aqueous state, they conduct electricity. For example, HCl. Okay, HCl is a polar covalent compound, but in aqueous state, which means that when we add water in HCl, okay, it is conducting electricity. Why it is conducting electricity? We have already studied, because this HCl gets ionized. Correct? In the starting of the video also we have seen it ionizes in H3O plus and OH minus ions. Correct? Sorry, H3O plus and Cl minus ions, not OH minus ions. This Cl minus ions. Now these ions, okay, they are actually free to move in water. These are mobile ions. So these mobile ions then conduct electricity, because we know what else is required for conducting electricity? Just free ions. Okay, we need just mobile ions and the electricity can be conducted, because we have already studied in electrolysis. These ions then move towards the respective electrodes and conduct electricity. Okay, so in this case also, see, HCl is an acid. In its aqueous state, it is producing free ions. That's why it is conducting electricity. Now moving ahead, let's see the chemical properties of acids. Okay, so chemical properties means we are just going to see the chemical reactions of acids. Very clear. So first, reaction of acid with metals. Now how acids react with metals? Dilute acids like HCl, H2SO4, okay, they react with metals to simply form metallic salts and hydrogen gases evolved. Okay, so just you have to remember this simple general equation, okay, simple general reaction, and you would be able to write the reactions. Okay, if suppose you are given that, suppose sodium is the metal and dilute acid is HCl, then write the reaction of sodium metal with dilute HCl. So you can simply write which metallic salt is going to be formed, okay, and hydrogen gas is going to be released. Very clear. So now let's see. Now one more interesting thing before seeing the reactions, both these acids, okay, in the dilute, this dilute HCl and dilute H2SO4, they react explosively with reactive metals like sodium, potassium, calcium, okay, and they react moderately with less reactive metals like magnesium and zinc. Okay, very clear. Now I am going to show you one reaction for dilute HCl. Okay, now I would take the example of sodium. So reaction of dilute HCl with sodium metal, okay, what would happen? We know metallic salt is going to be formed, hydrogen gas is going to be released. Okay, so first I would write the simple thing, hydrogen gas, okay, then metallic salt is going to be formed. Now which metallic salt would form? See here clearly, the hydrogen gas, okay, which is formed, this hydrogen is involved in its formation. So what is remaining? Sodium and chlorine, and we know sodium chloride, right? It is the metallic salt, or it is the salt. Okay, so we can just easily write down. Now let's balance it. So 2 hydrogen atoms, I would just make it 2 here. Then what happened? 2 chlorine atoms on that side. So here only 1 chlorine atom. So 2 chlorine atom. Then sodium. So only 1 sodium here, and here there are now 2 sodiums. So here 2 sodium I would make. Now everything is balanced. See, 2 hydrogens, okay, 2 chlorine, 2 hydrogens, 2 hydrogens, 2 chlorine, 2 chlorine, 2 sodium, 2 sodium. Okay, so in this way you have to balance. I know you know how to balance because you have studied in your previous grade. So when you write the reactions for other metals like potassium, calcium, magnesium, zinc, okay, you just need to write first hydrogen gas is getting liberated in all these cases, okay, and the salts, okay. So in case of potassium, and when there is HCl, okay, in all these cases, now potassium with HCl it would form KCl, calcium with HCl it would form CaCl2, calcium chloride, okay, magnesium with HCl it would form magnesium chloride, zinc with HCl it would form zinc chloride, okay, very simple. Now you have to just balance the reactions, that's it. Now we would see the reactions of metals with dilute H2SO4. Same like how they reacted with dilute HCl, they are going to react with dilute H2SO4 as well. So again the sodium's example, how it would react, it would form metallic salt and hydrogen gas. So hydrogen gas I'm writing here, it's getting evolved, and metallic salt, which metallic salt would be formed? See, the hydrogen atom would be involved in the formation of H2 gas. So what is remaining? Na and SO4. We know Na2SO4, right? Sodium sulfate. Okay, this is the salt which would be formed. Now here let's balance Na2. So here Na2, S1, S1, O4, O4, okay, and H2, H2. Reaction is balanced. So in the same way, if we would try to write the reactions for potassium, calcium, magnesium, zinc, okay, what would just change? This would remain exactly the same. Hydrogen gas is going to be released, okay. Just the number of hydrogen gas may change when you would balance, but hydrogen gas is going to be released. What would change is the salt which is formed in all these cases. Okay, in case of potassium, it would be like H2SO4 plus potassium it gives us the salt K2SO4. Okay, potassium sulfate. Just like sodium sulfate, potassium sulfate, calcium sulfate, CaSO4, right? Magnesium sulfate, MgSO4, zinc sulfate, ZnSO4. Okay, now I hope you know how to write the formulas of these compounds as well. Okay, it's very simple. See here, in case of, I'm telling you, for Na2SO4, Na forms Na plus, right? SO4 is in SO4 2 minus. So in order to balance the charges, we need 2 Na plus, right? So 2 plus 2 minus, now it's balanced. Now they combine and form the salt. So how would they combine? There are 2 sodium atoms now. So Na2SO4, see, Na2SO4. So same applies for all these metals as well. Okay, very simple. Now one more thing. In exams, they would simply ask you, sometimes they would ask you that if suppose potassium is treated with dilute HCl, okay, give one observation. So what you would write then? So you should absolutely first know what happens when potassium is treated with dilute HCl. So now you know metals when treated with dilute acids, they form metallic salt and hydrogen gas, right? So potassium when treated with dilute HCl, it would form potassium chloride and hydrogen gas. So you would reach till here. Now observation would be the hydrogen gas, right? It is getting involved. So no need to write directly. You should not write that hydrogen gas is getting involved. How you would know, right? In order to tell that hydrogen gas is getting involved, you need to tell some test for hydrogen gas. So test for hydrogen gas is very simple. When this reaction takes place, suppose when potassium is added to dilute HCl, okay, we know hydrogen gas is getting liberated. But now how to test it? So what we do is we take a splint. Splint is a simple wooden stick. Okay, we burn it slightly and then we bring that splint near the mouth of the test tube, in which this reaction is taking place, the reaction between potassium and dilute HCl. Now we know from the test tube, after the reaction, the hydrogen gas is getting released. So when we bring this splint near the mouth of this test tube, what happens is the burning splint extinguishes. Okay, it just gets off, turns off, it stops burning, and the hydrogen gas, it itself burns. You would find in the test tube, you would find a fire in the test tube, okay, a small fire like thing, and it would burn with a pop sound. Okay, so when you would find this is happening, then you can say that hydrogen gas is getting released. So what you can write in the examination, you know hydrogen gas is getting released, but you would write the test. So you would write a gas which extinguishes the burning splint and itself burns with the pop sound is released. Okay, now next reaction, the reaction with bases. Okay, so it's a very simple reaction. It's also very simple. Now acids, they react with bases and they simply form salt and water only. Okay, so I would take an example, very simple example of HCl. Okay, we know this is an acid. Now I would take a base, NaOH. Now both of them react, the acids react with bases and they form salt. Now here we know which salt would be formed. See, the Na and Cl, they would combine. Okay, Na plus and Cl minus, they would combine and they would form NaCl. Okay, so NaCl salt is getting formed and water is getting released. So see, H and OH, okay, they would combine again and they would form water. Very simple. Now balance it. Na 1 atom, chlorine 1, hydrogen 2. Okay, so here there are hydrogen 2 atoms, here there are also 2 atoms, and oxygen is 1, so it's balanced. Okay, and this reaction, okay, the reaction of acids with bases to form salt and water, okay, this reaction is called as neutralization reaction. Okay, now let's see the third reaction of acids. Okay, so the action of dilute acids. Now here we are going to take HCl and H2SO4. Okay, these two dilute acids, and their action we are going to see on salts. Okay, first was metals, then we came back to bases. Okay, the second reaction was with bases, and third is with salts. Now we are going to see three types of salts, okay, on which the dilute acids act. First is the carbonates and hydrogen carbonates, second is sulfites, and third is sulfites. Okay, so we are going to see it later on. First we are going to see the action of dilute acids on carbonates and hydrogen carbonates. Okay, now here specifically we are going to see metallic carbonates and metallic hydrogen carbonates. Now what does this mean? Okay, what are metallic carbonates? Very simple. Okay, for example, I can write here sodium carbonate. Okay, see here, sodium metallic carbonate, CO3, 2 minus radical. Okay, we call it as carbonate, right? CO3, 2 minus. Okay, so this salt is having this carbonate radical and a metallic ion, so metallic carbonate. Similarly, metallic hydrogen carbonate. Now same way you can figure out, it would be having a metallic ion, okay, and hydrogen carbonate radical. Okay, hydrogen carbonate, HCO3 minus. This is the hydrogen carbonate radical. Now for example, you can see NaHCO3, C, hydrogen carbonate radical and metallic ion, sodium ion. Okay, they combine, they form metallic carbonate, metallic hydrogen carbonate, sodium hydrogen carbonate. Very clear with examples. Now what these dilute acids do to this? Okay, this poor metallic carbonates and poor metallic hydrogen carbonates, I would just represent their general reaction like this. Okay, hydrogen carbonates, I am writing just the radical, okay, the main radical, the main difference between them. So this poor carbonates and hydrogen carbonates, when they are acted upon by the dilute acids like HCl or H2SO4, what is happening? They are getting decomposed. Okay, this metallic carbonates and metallic hydrogen carbonates, they break down. Okay, they break into salt, water and carbon dioxide gas. Okay, so here this carbon dioxide gas is getting released. Very clear. Now this is the general reaction. Okay, now let's see specifically one example and let's try to understand how this reaction is taking place. Okay, so I hope you are writing along with me. Okay, you are noting down these things because these are very much important, because this reactions, okay, the action of dilute acids on salts, these reactions are like the favorite topic of the people who set your exam papers, because lots of questions has been asked from this section. Okay, now what we are going to see now is the example. So I am going to take a simple example, calcium carbonate, CaCO3. Okay, now I would treat it with a dilute acid, say dilute HCl. Now what is going to be formed? We know this calcium carbonate is going to be decomposed, right? The decomposition is going to take place and it is going to decompose into a salt. Okay, I would write the salt later on. Next, what would be forming? Water and carbon dioxide gas. Okay, now which salt would be formed? See, can you just make out this calcium and this chlorine? Okay, water and carbon dioxide, see, hydrogen, carbon, oxygen, they are already involved in those two species. What is remaining is calcium and chlorine, so it would form calcium chloride. Very simple. Now you would just balance the reaction. So calcium 1 1, chlorine 2 2, hydrogen 2. Okay, so hydrogen here there are 2, then there on that side oxygen are 3 atoms. Okay, here oxygen 3 atoms, carbon 1, again here carbon 1, and oxygen we have already balanced. Okay, so I did whatever you write the reaction after that, make sure that you balance it, otherwise you would lose marks. Okay, never forget that. This is the last step of the reaction, writing a reaction. Now what you do is, now you try to write the reaction of calcium carbonate with dilute H2SO4. Okay, just give it a try. Pause this video and give it a try. Okay, so I hope you would have tried. So what your answer would be, I would write it here: calcium sulfate, water, and carbon dioxide molecule, and carbon dioxide is released. Okay, but it's very, I'm like feeling very disappointed to tell you that this reaction will not take place. Okay, now why is this so? This is the twist in the story. See, the salt which would be formed, if you have written it rightly, it would be calcium sulfate, right? But since this calcium sulfate salt is insoluble in water, okay, therefore the reaction does not take place. Okay, so this reaction does not take place. So such reactions in which the salt which is getting formed, if it is insoluble, those reactions will not take place. For example, we will see another examples like lead carbonate. Okay, when this lead carbonate reacts with dilute HCl and dilute H2SO4, so what it would form? It would form the salts. First, let's write the salts itself. So salts would be lead chloride. Okay, now here this hydrogen and CO3, hydrogen, carbon and oxygen would be involved in forming water and carbon dioxide. So remaining is lead and chlorine. So lead chloride, same way hydrogen, carbon, oxygen would be involved in forming water and carbon dioxide. So remaining is lead and sulfate. So lead sulfate, PbSO4. Now both of these salts both of these salts are also insoluble. Okay, so these reactions also don't take place. Very clear? Okay, so far we have seen the reaction of dilute acids on metallic carbonates. Now we are going to see the reaction of dilute acids on metallic hydrogen carbonates. Okay, so I would write here calcium hydrogen carbonate, metallic hydrogen carbonate, CaHCO3 twice. Okay, now when it is reacting with dilute HCl, now you give it a try. Okay, what would be forming? The same thing. What was forming with carbonates, it would be same thing would be forming with hydrogen carbonate, salt, water and carbon dioxide. Pause the video here and give it a try. I'm telling you right now that this reaction would take place. Okay, and why it would take place? Because the salt forming is calcium chloride. Okay, calcium chloride. See here, the hydrogens, carbon and oxygen, they are involved in the formation of water and carbon dioxide. Okay, gas. Rest things which are left are calcium and chlorine. Okay, these two are remaining. So calcium chloride would be formed and it is soluble in water. Therefore, this reaction would take place. Now, what you would do is you just balance this reaction, see whether it is balanced or not. Calcium 1, calcium 1. Okay, so chlorine here there are 2. So I would make here 2 chlorine atoms. Then hydrogen 2. Okay, hydrogen 2 and here 2. So 4 hydrogen atoms on this side. So I would make it here 4. Then oxygen became 2 oxygen there. 2 oxygen there, 4 oxygen atoms. Okay, so here 3 to the 6 oxygens, right? Now I should make there 6 as well. Here there are 6, and here there are 4. So how would I make 6? So here there are already 2. I would just multiply this carbon dioxide with 2. So what would happen? See, 2 oxygen and 2 to the 4 oxygen. So 2 oxygen plus 4 oxygen, 6 oxygens. Okay, and next is 2 carbon atoms. Okay, after oxygen we are moving to carbon atom. So one by one we are seeing all the atoms. After calcium, chlorine, then hydrogen, then oxygen, and then lastly carbon. Carbon atoms are 2, and here you can see carbon atom is also here. See, 2 carbon atoms. Okay, very clear. Now moving ahead, let's come back to this salt. Okay, sodium hydrogen carbonate. Now try to remember. Okay, I will definitely know that maybe you won't remember, but at the starting of this chapter, okay, when we studied why actually to study this chapter, I have told you that when ant bite you would experience, you have to apply baking soda, the paste of baking soda, and this is what the formula of baking soda: sodium hydrogen carbonate. Okay, so this sodium hydrogen carbonate, I told you at that time that it just reacts with the formic acid. Okay, now you also know the formic acid's formula, HCOOH. Okay, so it reacts with the formic acid and it reacts in such a way that the formic acid gets used up. That's why we feel less irritation, right? We feel relief. And see, this sodium hydrogen carbonate, it is reacting with this acid, okay, in the same way, okay, like it is reacting with HCl and H2SO4, it would react in the same way, okay, to form salt, water and carbon dioxide. Okay, gas would be there. The hydrogen, carbon, oxygen, okay, and this hydrogen and this hydrogen, carbon and oxygen atoms, they would be involved in forming water and carbon dioxide. Rest, whichever thing is remaining, see this HCOO part, this is the minus, negative part, okay, this is the plus part. So HCOO minus, H plus, okay. So this H plus will move on, this HCOO minus would go here and it would combine with Na plus and it would form HCOO-Na. Okay, this salt would be formed and along with it water would be released and carbon dioxide gas is also released. So in this way this formic acid is getting used up. Okay. So whether to see balance, it is balanced or not, sodium 1, 1, hydrogen, there are 3 hydrogen atoms. So there are also 1, 2, 3, right? And then carbon 1, 2, okay? And on that side, carbon 1 and carbon 2. Okay, fine. Then oxygen 3, 4, 5, 2, 3, 4, 5. Very clear. Then again hydrogen we have already balanced it. Again carbon, already balanced it. Again oxygen, already balanced it, and hydrogen. So we have balanced the equation. Okay, so this is how the irritation because of that ant bite we experience, it just leaves off. Okay, now next is the action of dilute acids on the next type of salts we are going to see, which are sulfides. Okay, metallic sulfides. Now same way they are also going to get decomposed. Decomposed means break down. Okay, so these salts, metallic sulfides. Now what actually are these? There would be a metallic atom, right? And there would be a SO3 2 minus radical. Okay, so metallic ion and SO3 2 minus radical would be there and it would form a metallic sulfide salt. Okay, N here corresponds to 1, 2, 3, anything, because some metallic atoms are having Na plus 1, right? Magnesium is having Mg2 plus, right? So that's why I've written N. Okay, Mn plus. Now suppose for example I'm writing Na2SO3. Okay, this is sodium sulfide, the example of metallic sulfide. Now what is happening? These are getting broken down into salt, again water, and here carbon dioxide is not getting released. Just like in carbonates and hydrogen carbonates, in that case carbon dioxide was getting released. Here in case of sulfide, sulfur dioxide is getting released. Very simple. Similar way, salt, water and carbon dioxide was getting produced in that reaction. Here salt, water and sulfur dioxide is getting produced. Okay, in this reaction sulfur dioxide. And the reaction of, here I would write, okay, I'm just representing this. Okay, you can either write in word form, metallic sulfide, to make it very simple. Okay, metallic sulfides reaction with dilute acids. So dilute acids react with metallic sulfides. These metallic sulfides undergo decomposition. They break down into salt, water and sulfur dioxide. So let's see an example. So calcium sulfite, when it reacts with dilute HCl, what would happen? Water and sulfur dioxide is already getting formed, we know. So we would write it. Okay, simple products we are going to write it first. Then we would apply our brain and form a salt. So see here, hydrogen, oxygen, sulfur. So hydrogen, oxygen, sulfur, just forget about them because they are involved in water and sulfur dioxide formation. So what is remaining? Calcium and chlorine. Calcium chloride would be formed, CaCl2. Now what you have to do is just balance the reaction. So calcium 1, chlorine 2, hydrogen 2. Okay, so here hydrogen 2, oxygen 3, sulfur 1. So oxygen 3, sulfur 1. It's balanced. Very clear. Now moving ahead, the action of dilute acids on metallic sulfides. Okay, now what are these metallic sulfides? Same way, now you would be knowing sulfides. Okay, they are having S2 minus ion. Okay, sulfide salts. Now metallic sulfides means there would be a metallic ion along with a sulfide ion. It would combine and form metallic sulfide. For example, I would write here sodium sulfide. Okay, Na2S. Okay, now you know how to write the compound formula, I hope. Okay, so what happens when dilute acids are acting on this metallic sulfides? They are decomposing them. Okay, so I would just write here dilute acids when react on when react with metallic sulfides. I'm writing in the word form, so it would be easy for you. Okay, dilute acids react with metallic sulfides and they decompose these metallic sulfides into simply salt and hydrogen sulfide gas. Okay, H2S gas is called as hydrogen sulfide gas. Very simple. Let's take an example to understand this thing. So I'm taking example of zinc sulfide. Zinc sulfide, I'm treating it with dilute HCl. Okay, what is happening? Salt would be formed, hydrogen sulfide gas is released. So hydrogen sulfide, I would write it first here. Then I would make a salt. So for hydrogen sulfide, hydrogen sulfur would be getting used up. So hydrogen and sulfur, they are getting used up. What is remaining? Zinc and chlorine. So ZnCl2 would be formed. Zinc chloride. Okay, zinc chloride. Now balance it. 2 chlorine atoms. Okay, 1 zinc. Here 1 zinc, 2 chlorine, 2 chlorine, 2 hydrogen. Okay, 2 hydrogen, 2 hydrogen. Sulfur 1, sulfur 1. Okay, it's balanced. So this is the general reaction which you have to always remember. After that, you can make the you can write the reaction very easily. Now one more interesting thing, when sometimes they would ask you question that what happens, or give one observation, just like the same case. Okay, we have seen for the reaction of dilute acids on metals. So same way they would ask that dilute HCl is reacting with zinc sulfide. Okay, give one observation. So what would be the observation? The zinc chloride is getting formed and hydrogen sulfide gas is formed. So observation would be hydrogen sulfide gas is formed, right? But you don't need to write the name of the gas. You just need to write the what you observe. And hydrogen sulfide gas, the test for detecting this gas is itself, this gas is having such a bad smell that you would detect it very quickly. Its smell is like rotten egg. Okay. So when you experience this rotten egg smell anywhere, you can just confirm that in that reaction, when the reaction is taking place and you experience a rotten egg smell, so you just can definitely say that hydrogen sulfide gas is getting formed. Okay, so what would be your observation? You would simply write a gas with rotten egg smell is evolved or liberated. Very simple. So friends, so far we have seen the properties of acids, both physical and chemical. Now it's time to see the properties of bases. Okay, and starting with the physical properties, first is taste. So bases taste bitter. Okay, now it's very simple to remember their taste. Bases B, bitter B. That's it. Okay, but don't try to taste it. They are very much dangerous. Okay, it's very much dangerous to taste them. Now next is the effect on skin. Just like acids have corrosive action. Okay, we may experience very painful burns and blisters, but in case of bases, they also have corrosive action, but the corrosive action is mild. Okay, so we may experience slight burns. Okay, next is bases also conduct electricity like acids, and they conduct electricity in their aqueous state as well as in their molten state. Okay, so for example, let's see the example as NaOH. This is a base. We know when we add it in water, it dissociates into its ions. We have just now seen, we have seen in the previous video. Okay, we have studied about them when we are studying bases and their dissociation. Okay, so they dissociate into its ions Na plus and OH minus. Okay, in water. Now these ions Na plus and OH minus are free to move, right? They can move, they can dance here and there. So these free ions, what else we require for conducting electricity? Just the free ions. So these free ions move to the respective electrodes and conduct electricity. Okay, same way when our NaOH, okay, now it is in solid form. NaOH exists in solid form, in pellet form. Okay, like small tablet form. Okay, so this NaOH, when we heat, okay, and we bring it into the molten state, since this is an ionic compound, it dissociates into its ions. Okay, in Na plus ion and OH minus ion, and again these ions are now free to move, right? So they again move to the respective electrodes and conduct electricity. Okay, so in this way they conduct electricity. Now if you want to know in much more detail how they move to the respective electrodes and all those things, we are going to learn about it in electrolysis, and also we have learned it in slighter details in your chemical bonding chapter. Okay, you can refer that video of ionic bonding. Okay, if you have missed it, you can go back and see the ionic bonding video, in which in the dissociation part I have told you about how the ions move to the respective electrodes. Okay, in electrolysis. Now moving ahead, bases are soapy substances. They are slippery to touch. Okay, now why is this so? See, let's take an example. The NaOH, we know, I have told you, this is used for making soaps, right? And how it forms soap? It combines with oil and then forms soap. Now see, this base, okay, combines with oil and forms soap. Now on our skin as well, okay, if very much dilute NaOH falls on our skin, what happens is it reacts with the oil on our skin. Okay, oil, like it is in the form of fats, okay, on our skin. So this NaOH reacts with that oil, okay, and it forms soapy solutions. Okay, so these soapy solutions, we know they are like slippery to touch. Many a times you would have experienced a slip in bathroom or something like that, because the soapy solutions make the floor slippery. So in the same way, soapy solutions are formed on our skin, and therefore we say that bases are slippery to touch, or they are soapy substances. So question may arise in your mind that, sir, you said that on skin it has mild corrosive action, we may experience slight burns, and you are again saying that it is slippery to touch. So what's actually the thing? See, very dilute bases, okay, if they fall on the skin, then we may feel the slipperiness. But the concentrated bases, okay, like concentrated NaOH, if it falls on our skin, then definitely we would experience burn. Okay, so now after the physical properties of bases, let's move on to the chemical properties of bases. Now you know what we are going to study. We are going to study the reactions of bases. Now first is reaction of base with carbon dioxide. Okay, so now at last, once we learn this reaction, I would tell you an interesting application of this reaction. So first let's see what happens. Strong alkalis, now we know which are the strong alkalis: NaOH, KOH, right? So these strong alkalis, they absorb the carbon dioxide from the air, okay, and they form carbonates. Okay, so what is the general reaction? Simply, strong alkalis, okay, they absorb carbon dioxide from the air, they form carbonates. Now we know carbonates are having CO3 minus radical, correct? So they form carbonates and they simply form water. Okay, so let's write the reaction. Very simple. So NaOH plus CO2, it would give me carbonate of sodium, right? Carbonate. So CO3 should be there. So I know carbonate of sodium is sodium carbonate, Na2CO3. I wrote it down very simply. And water. Very simple. Okay. Same goes with KOH. You can try. The product would be, in case of KOH, K2CO3. So potassium carbonate and water. Okay. Now what you would do is you would just simply balance this reaction. Okay. I would leave it to you. You can better do this. Okay. Now, what is the application of this reaction? See, when you would keep these strong alkali solutions, okay, in your lab open, so you can just relate this thing, that if they are kept open, what they would do, they would absorb the carbon dioxide molecules, right? Carbon dioxide gas molecules which are present in the air, right? Which we are just giving out when we breathe. And these carbon dioxide molecules, they would absorb and they would form Na2CO3 or K2CO3. Okay. So what would happen? Our NaOH and KOH solution would not be the pure solution. Exactly. So what you would do, you now know that, oh, this reaction takes place, okay, when we keep open NaOH and KOH. So what you would do, you would just close whatever container in which you are keeping this NaOH and KOH to maintain the purity of your alkali, strong alkali, NaOH or KOH. Very simple. Okay, now let's move ahead to the next reaction of bases, the reaction with acids. Okay, now bases react with acid. And how they react with acid? They react with acid to form simply salt and water. Okay, now I would just write the initials. Bases react with acid, they form salt and water. Now example, I think you could write on yourself. We have seen the example, okay, we have seen this reaction, exactly the same type of reaction, okay, neutralization reaction in case of acids as well. Acids react with bases, okay, acids react with bases to form salt and water. Same way, we are just writing it in the opposite manner. Bases are reacting with acid to form salt and water. Both the things are exactly the same. Okay, so I would here take the example of base NaOH, example of acid HCl. Now you can pause the video here, you can try on your own to write the products of this reaction. It is NaCl and H2O. Okay, and we have already seen how it is getting formed. Okay, in that reaction, where we studied the reaction of acids with bases, and this reaction is also called as neutralization reaction. I have already told you the reaction of acids with bases or bases with acids to form salt and water is neutralization reaction. Okay. Now the last reaction of bases, the reaction of bases with ammonium salts. Okay. Now what are these ammonium salts? This salt would be made up of ammonium ions. Okay. So there would be ammonium ion and there would be some negative ion or negative radical with which this ammonium ion would combine and it would form an ammonium salt. Okay, in this way. So for example, NH4Cl. Okay, NH4 plus Cl minus would combine and it would form NH4Cl. Okay, so what happens now? This alkalis, okay, they react with our ammonium salts. I'm writing here NH4X. Okay, and we need to heat them up. Okay, we need to warm them. Okay, this mixture. So when these alkalis are heated with ammonium salts, the heating process, okay, we denote in the reaction with a triangle on the arrow. Okay, very simple. So alkalis, when they are heated with ammonium salts, they give us, just like we have studied in the case of acids, salt, water, and the gas is released, right? Carbon dioxide gas in case of carbonates and hydrogen carbonates. In case of sulfides, it is sulfur dioxide gas, right? So in the same way here, salt water would be formed and ammonia gas is released. Okay, so why I'm just telling the things, okay, again, when I see a similar type of reaction, I just try to make you remember the reactions which we have learned, which are also of similar type, so that you can correlate it, okay, so that you can easily remember it. Now, let's take an example to understand this. So I'm taking an example of alkali as NaOH, salt as NH4Cl, and I would heat it, okay, I would warm up, and then I know water and ammonia is going to be formed, ammonia gas is going to be released, and the salt is going to be formed. Now see, here NH4, okay, this thing is going to be involved, this nitrogen, hydrogen, okay, this atoms, nitrogen, hydrogen are going to be involved in formation of ammonia, so we'll just leave them. Okay, hydrogen and oxygen are going to be involved for formation of water, so leave them as well. So what is remaining now? Remaining is the sodium and chlorine, right? Sodium and chlorine. So what would be formed? Which salt would be formed? NaCl. Very simple. Now just balance this reaction. Okay, so Na, then chlorine. Okay, one sodium, one chlorine, one sodium, one chlorine, hydrogen, 2 plus 3, 5 hydrogens. So here see 4 hydrogens and 5 hydrogen, 1 oxygen. Okay, so here 1 oxygen atom, and then nitrogen is also 1. So here also nitrogen is 1 nitrogen atom. Okay, this is sodium, Na. Okay, this is nitrogen atom, and the hydrogen atom we have already balanced it. So this is balanced reaction. Okay, so friends, so far we have seen the properties of acids, properties of bases. Now moving to the last concept of this chapter, which is the pH scale. Okay, so how we came to the point where we felt the need to devise this pH scale, and what actually this pH scale is. Okay, so let's start to understand, to learn this story from the self-ionization of water, right? We have studied this self-ionization in coordinate bonding, correct? So if you have missed that video, okay, then you can go back and see what actually the self-ionization of water is. Okay, so I have explained the self-ionization in very much detail in that video. So I would just simply write the equation for self-ionization here. Okay, and we know that self-ionization of water yields us hydronium ion and hydroxyl ion. Okay, so this is taking place in just water. Okay, if you take a beaker and you pour some water, so in that some water molecules will get ionized, okay, and they would form hydronium ions and hydroxyl ions. Okay, now see the number of hydronium ions and hydroxyl ions. For one hydronium ion, one hydroxyl ion is produced. Okay, so the net number, okay, whatever would be the number of hydronium ions and hydroxyl ions produced, so the number of hydronium ions and number of hydroxyl ions are exactly the same, right? Since they are exactly the same, so we can say that the amount of hydronium ion and amount of hydroxyl ion is same, right? And when we can say the amount in a more correct term, okay, which is concentration. Okay, so instead of saying the amount of hydronium ion and amount of hydroxyl ion, we can say the concentration of hydronium ion and concentration of hydroxyl ion here. Okay, so what we found that the concentration of hydronium ion and concentration of hydroxyl ions are exactly the same. So what you can say is, see, we can represent this concentration word, no need to write it all along all the time, okay, by the square brackets, and whoever's concentration you are representing, you just write it down in that square bracket. Okay, so concentration of hydronium ion and the concentration of hydroxyl ion, okay, they are same in the pure water, and that's why, see, the positive and the negative charges are same. So we say that water is neutral. Okay, we know atom is also electrically neutral because the positive and negative charges are exactly the same. So in this case also, water is also having the positive and negative charges exactly the same. So we say water is neutral in nature. Okay, now this was the case of just the water. Now we are going to make some changes in this water. Now we are going to do some interesting things. Okay, so I'm having this same water. Now I'm going to add a salt in it. Okay, now salt, such salt which is made up of strong acid and strong base, okay, which is an NaCl. Now how it is, see, just now we have studied the neutralization reaction, and deliberately I have taken up this reaction because in this reaction only we have studied NaOH plus HCl gives us NaCl plus H2, right? See, NaOH is a strong base, strong alkali, HCl is a strong acid. So this salt is made up of strong base and strong acid. Okay, now what happens when we take a salt which is made up of strong base and strong acid and we add this salt in water? Okay, let's see the story. Okay, so when I'm adding this, we have already studied this in the chemical bonding, okay, in the ionic bonding part. So this NaCl is an ionic compound, and when we add this NaCl, okay, in water, so I'm writing here aqueous because I have added it in water, it forms Na plus and Cl minus ions. Okay, aqueous. Very clear. Now these ions are formed, so we actually say that this NaCl is getting dissociated into its ions. So here there are hydronium ions and hydroxyl ions as well, okay, in water, because the self-ionization is taking place, though it is taking place in very less amount, but still the hydronium ions and hydroxyl ions are present. Now we have added NaCl, and now Na plus and Cl minus ions are also present. Okay, now what happens is, see, these Na plus and Cl minus ions, you can understand in this way, they are being surrounded by the water molecules. Okay, the water molecules. So leave about them now. Now they are not doing anything to our hydronium ions and hydroxyl ions. Okay, so now our hydronium ions and hydroxyl ions are still in the same concentration, right? Still in the same concentration, and such solutions which are having hydronium ions concentration and hydroxyl ions concentration exactly the same, okay, are called as neutral solutions. Now why I'm calling here the solution word, because we have added NaCl in water. Okay, now it's a solution. Okay, so just now we studied neutral solutions are having hydronium ions concentration equal to hydroxyl ions concentration. Now let's move on to the second part of the story, that what would happen when we would add a acid in the water. Okay, so again I'm having this beaker. There are hydronium ions, hydroxyl ions in this, okay, because this beaker is full of water. Now I'm adding acid, suppose HCl. Now this HCl, what it does, we already know, right? We have studied this HCl's ionization in water, right? Just now when we studied about acids, how HCl ionizes, it's a strong acid, okay, so therefore normal arrow, and it ionizes to form hydronium ions and chloride ions, correct? So now this hydronium ions and chloride ions would be formed. Now leave about the chloride ions right now here, but we are now interested about hydronium ions, because actually there are already some hydronium ions and hydroxyl ions, but now extra hydronium ions are there also. Okay, now because of adding the HCl, hydronium ions are getting produced, and now what would happen? See, the hydronium ions concentration would increase, correct, right? You're getting this? So hydronium ions concentration is increasing. when we are adding acid. Okay, and at the same time what is happening is hydroxyl ions concentration is decreasing. Okay, now we have just now seen why hydronium ions concentration is increasing, because of we are adding acid. But now why hydroxyl ions concentration is decreasing? Okay, so don't worry about it right now. When you would study in your higher grades the chapter of equilibrium and the Le Chatelier's principle, so at that time you would actually know why this hydroxyl ions concentration decreases. Okay, so for now you just remember that when we add acid, hydronium ions concentration increases. You have understood this. But at the same time hydroxyl ions concentration decreases. Okay, now what would happen? See, initially the hydronium ions concentration and hydroxyl ions concentration was same before the acid was added. Now the hydronium ions concentration has increased, hydroxyl ions concentration has decreased. So you can clearly say that now hydronium ions concentration has become greater as compared to hydroxyl ions concentration, right? See here. Okay, suppose there was one molecule of hydronium ion and one molecule of hydroxyl ion. Okay, one ions were present. Now there are two hydronium ions and one hydroxyl ion. Okay, so we can clearly see, we can clearly understand by this that since hydronium ions concentration is increasing, hydroxyl ions concentration is decreasing, so hydronium ions concentration would be more. Okay, previously it was same, now it would increase, now it is increasing, this is decreasing. So now this hydronium ions concentration is greater than the hydroxyl ions concentration. Okay, and such solutions which are having this hydronium ions concentration greater than hydroxyl ions concentration are acidic solutions. Okay, which are formed when we add an acid in a water. Okay, just now we have did this thing. Now let's add a base. Why to wait for the base, right? So I'm adding a base NaOH in water. Now what would happen? Already there are hydronium ions and hydroxyl ions. The same story. Base would dissociate, our NaOH, okay, would dissociate again into Na plus and OH minus ions. We already know this thing. Okay, we have studied this. Now what would happen? Here the Na plus and OH minus ions are also getting formed. Now forget about Na plus. We can ignore this. Just concentrate on this OH minus ions which are getting formed. So what would happen? The OH minus ions concentration would increase now. Same way, just like the hydronium ions concentration was increased when we added acid. So here OH minus ions concentration is increasing when we are adding base. And at the same time, hydronium ions concentration goes on decreasing. Why? I have already told you would learn it when you would learn equilibrium and Le Chatelier's principle. Okay. So what is happening? What is happening? Hydronium ions concentration is increasing, hydroxyl ions concentration is decreasing. Initially it was the same. Okay, but now hydroxyl ions concentration is increasing, hydronium ions concentration is decreasing. So what would happen? Hydroxyl ions concentration would become more than the hydronium ions concentration. Okay, now we can just write it in the opposite format. Hydronium ions concentration, okay, is becoming less than the hydroxyl ions concentration. Okay, and such solutions in which the hydronium ions concentration is less than hydroxyl ions concentration are basic solutions. Okay, which are formed when we add a base into water. So let's summarize the story, whatever we have learned so far. In neutral solutions, we have learned that hydronium ions concentration is equals to hydroxyl ions concentration. Okay, in acidic solution, hydronium ions concentration is greater than hydroxyl ions concentration. Okay, and in basic solutions, hydronium ions concentration is less than hydroxyl ions concentration. Okay, very clear. Now you can make out that for an aqueous solution, okay, aqueous solution means the solution which is formed by using water. So for that solution, the nature of that solution, whether it is neutral, acidic or basic, it's depending on the concentration of hydronium ions here, right? And in order to express this hydronium ions concentration in the aqueous solution with ease, okay, that time we felt the need for some scale. Okay, and that's why our very, very interesting Danish biochemist Sorensen devised the scale which is called as pH scale, okay, in order to represent the hydronium ions concentration in the aqueous solution, okay. And with the help of this pH scale, we can also tell whether the particular solution is acidic, basic, which means alkaline, or neutral as well, okay. Now what does this pH in this pH scale word means? Okay, so here the P word, okay, has been derived from potens word, and this potens is a German word which actually means power, okay, power. So what does this pH means? pH means power of hydrogen. Now what is actually the pH of a solution then? Okay, so pH of solution is simply negative logarithm, okay, to base 10. We write it in this way. We write 10 at the base of this G, okay, of hydrogen ions, okay, concentration, negative logarithm to the base 10 of hydrogen ions concentration, which is expressed in moles per liter. Moles per liter is the unit for expressing concentration, okay. Now you would be surprised now where this hydronium ion has been vanished. Till now you were talking about the hydronium ion. Now why you have taken this hydrogen ion? Okay, so simply we already know that this hydronium ion is formed when this hydrogen ion combines with water, right? And it forms a coordinate bond with oxygen and the hydronium ion is formed, right? So that's why we have replaced this hydronium ion with hydrogen ion. Very simple, okay. Now, before moving on to the application of this formula, okay, let's see actually the pH scale. We are talking about this pH scale only, right? Now, let's study actually how this pH scale looks like. So, it's very interesting. See, the pH scale starts from 0, ends on 14, okay, just like the ruler you are having in your compass box, okay, in your geometry box. So, it is still 15. So, here 15 centimeters, here it's not centimeters here, but it's from 0 to 14, okay. Now, at the center, okay, don't mind if I haven't hit the center of this line. So at the center there would be 7, right? And if the particular solution's pH is 7, we say that that solution is neutral, okay. If the particular solution's pH is less than 7, suppose if it is 1, 2, 3, 4, 5 or 6, okay, so we call that solution as acidic solution, okay. And if the particular solution's pH is, now you would have guessed it, right, 8, 9, 10, 11, 12, 13, okay, that solution is alkaline or basic solution, okay. Now one more interesting thing, as we move on the pH scale below the 7, like if suppose the solution is having pH 6, now again the solution's pH change to 5, then to 4, then to 3, and the same solution's pH went to 2, then we can say that the solution is becoming more and more acidic, okay. But now when we are having a solution whose pH is 8, okay, that particular solution's pH is becoming now 9, 10, 11, 12, 13. So when we are moving after 7 from 8, 9, 10, 11, 12, 13, okay, so that particular solution we can say that that solution's alkaline nature is increasing, is becoming more and more, okay, or it is increasing. So very simple thing about the pH scale. Now let's see the application of the formula which we have seen. pH is equals to negative log to the base 10 of H plus ion concentration, which is expressed in moles per liter. So if I'm having this H plus ion concentration, I can tell the pH of the solution, okay. So how come? See, suppose let's see a question, okay, the H plus ion concentration is 10 raised to minus 4 moles per liter, okay. Find the pH of the solution. So we'll simply put the hydrogen ions concentration in this formula. So pH is equals to minus log to base 10, hydrogen ions concentration is 10 raised to minus 4, right? So I have just inserted the 10 raised to minus 4 there. Okay, and now we will just solve it. So how come we are going to solve? Whatever the power is there, 10 to the power minus 4. So that power we are going to bring it ahead of the log. Okay, so I'm just writing the negative sign here. I would bring the entire power term, okay, minus 4 term ahead of the log, and then I would write log base 10, okay, and then here 10. So whenever you would find log base 10 to 10, okay, it's actually 1. Very simple. So minus of minus 4 into 1, what would happen? Minus of minus 4 is plus 4. So pH of the solution is 4. Okay. Now, if you would have reverse, if you would think, sir, if I am given the pH of the solution, now I need to find the hydrogen ions concentration. How would I find then? So we would just make some changes in this formula. Okay. And this formula becomes in this way. Hydrogen ions concentration is equals to 10 raised to minus pH. Okay. Now, if you would have been given pH of the solution is suppose 6, find the hydrogen ion concentration. So you simply put here 10 raised to pH is 6. So 10 raised to minus 6. So hydrogen ions concentration would be very simple, 10 raised to minus 6. And since it is concentration, don't forget to use the unit moles per liter. Now here I would tell the significance of this unit. Okay, what does this moles per liter means? 10 raised to minus 6 moles are present in 1 liter of the solution. Okay, so this is the actual meaning, and moles is actually the unit. Okay, just like atoms, molecules, mole is a unit, but that unit means, okay, 1 mole means 6.022 into 10 raised to 23 particles. Okay, now these particles can be atoms, molecules or ions, depends. Now here we are talking about hydrogen ions, so 1 mole means 6.022 into 10 raised to 23 hydrogen ions. Okay, so this is a unit actually. Now moving on to the next interesting topic, it's related to the pH, yes, and here we are going to see how to test whether a particular solution is acidic, whether the particular solution is neutral, or whether the particular solution is alkaline or basic. Okay, so first we are going to use very simple methods. So first is pH paper. Okay, so this paper you can see here, on the screen, it looks like this orangish color. Okay, it's like quite yellow. I can draw the yellow one, but it's like something near to the orange color paper. Okay, now what we do is, if you are having some solutions which are having different pH, okay, so we need to find out now the pH of that solution. Once we know the pH of the solution, we can easily say whether it is acidic, neutral, alkaline, correct? So what we do, we insert this pH paper, okay, in that solutions. So first, suppose I am having these 2 solutions. Now I am going to insert these 2 pH papers in these solutions. Now what would happen? This pH papers shows different colors, okay, when we are dipping it into the solutions having different pH. Okay, now what we have to do, suppose for example I have dipped this pH paper, okay, and I have taken out. So whatever portion was dipped, I found this green color. Okay, and in the same way, suppose I have also dipped this pH paper in this solution. Okay, it is having different pH, and after taking out this paper, okay, this portion was dipped, so this portion of the paper got this dark bluish color. Okay, now what I would do, I would be having a paper on which there would be different colors. Suppose now this is the one color, okay, this is the another color, okay, and in front of that color particular pH value is written. Okay, so we would just match the color with the color which we have found on that pH paper, and then we would get the value of the pH. Now suppose if the pH value, whatever value we got, if it is below 7, then it is acidic, right? If it is below 7, if it is above 7, we know it is alkaline or basic. If it is 7, then we know it is neutral, right? So this is the simplest way in order to find the pH of the solution. Okay, now second way to know the pH of the solution is simply we can use universal indicator. It is a solution. Okay, now what actually this universal indicator is? So first let's understand the meaning of the word indicator. Okay, so indicator means you can just figure out from the word itself, it is indicating something. Now we are learning something, like we are learning the context, which is we want to test whether the particular solution is acidic, basic or neutral, right? So these indicators are the substances which are indicating us whether the particular solution is acidic, basic or neutral. Okay, and how they are going to indicate us? They are going to indicate simply by showing the change in their color or by showing the change in their smell. Okay, now let it be the part of smell. Let it go now because we are going to learn it at the last. Now we are using these indicators, okay, and the indicators which are dyes, okay, we are using it, we are mixing this indicator dyes, and this mixture of indicator, okay, we are forming a solution of it, and this is called as a universal indicator. Okay, suppose now what does this do? This also gives different colors in the solutions of different pH, just the same like the pH paper. The pH paper would get different colors. What universal indicator does is, when we pour the universal indicator, suppose these are the beakers, okay, which are having the solutions at different pH. Okay, now I'm pouring the universal indicator in these solutions. So what would happen? The solution would get different colors. Suppose after pouring the universal indicator, this got dark blue color. Okay, now I'm pouring the universal indicator in this, so it got green color. Okay, and then in this, okay, it got some light green color. Okay, you can make out, I think you can't make out, but yes, this is light green color. Yes, now so what we would do, simply just like the same case of pH paper, now we would just match the color of these solutions with a reference, right? We are having some paper, we would be having a paper, okay, on which the particular colors are given and the particular pH value is given in front of that color. So we would know that yes, this solution was having this much pH, this was having this much pH, this was having this much pH, and from the pH value we can know that whether the particular solution is acidic, basic or neutral, right? We already know it. How? So friends, we know that how to now find the pH of the solution by using a universal indicator solution. Okay, now I have told you about the reference paper, right? We are having some reference paper and we then compare the color of the solution. Okay, the color of the solution we got after adding the universal indicator into it, right? And we compare that color with the particular pH value. Okay, in front of that color the pH value is written, and then we get to know that that particular solution is having that particular pH. But actually we know that we have to remember actually that which color corresponds to which pH value when we add universal indicator into a solution. Okay, so it's very simple to remember. I'm going to tell you a trick as well. With the help of pH scale, we are going to remember that colors. Okay, that which particular color is denoting us or indicating us that the particular solution is having that particular pH value. Okay, so starting from 0 ending to 14, we know pH value, pH scale, and then here neutral. Okay, 7. Don't mind if I haven't placed the 7 exactly in the center of this line. So this 7 pH, okay, we know neutral. But when we add universal indicator into a solution and when we get a green color, then we say that that particular solution is having pH 7. Same way, now we are going to remember the colors with the help of trick. So when you move beyond 7, okay, towards 14, you make the colors cooler. Okay, cool colors. You know what are cool colors, what are warm colors. Blue and all those shades are cool colors, right? Red and all those shades are warm colors. So I'm making cooler, so I'm making it. So how I would make cooler? I would just skip one pH value, jump on the next pH value. So from 7 I would skip 8, jump on to the 9, and that 9 pH value, okay, is having blue color. Or we can say that the blue color is indicating that the particular solution is having 9 as a pH value. Then again I'm going to skip one value, I'm going to jump on the next value, okay, by skipping one, and I'm going to make the color more cooler. Okay, so from blue I'm going to make it indigo. Okay, and then again skipping one pH value, moving ahead to the next one, I'm making it violet. Okay, so now we are done with it on this side. Now we are moving backwards. Okay, so from 7 to 0, when we are moving, the same logic we would apply. I would just skip one pH value, jump on to the next one, and then I am going to make the color warmer. Okay, so from green to yellow. Okay, same way, skipping 4, moving to 3. Now it becomes pink. Okay, and then again 2, 1. Okay, Now this one has more warmer color, okay, which is red. So if you are having yellow, pink, or if you are getting yellow, pink or red colored solution after adding universal indicator to it, then this means that the pH of that particular solution is 5, 3 or 1 respectively. Okay, whatever color we get, we can just match it with it. Okay. Now one more interesting thing, we can use pH paper, okay, in case of a colored solution as well as colorless solution, to find the pH value of a colored solution as well as colorless solution. Now in case of universal indicator also, we can use it to find the pH value of a colored solution as well as colorless solution. Okay, but in case of universal indicator, one more interesting thing is when we are using colorless solution, okay, so the level of accuracy, okay, for the particular pH value is high, but when we are using colored solutions, the level of accuracy, okay, that for a particular pH value we are getting, that is low. What does it mean? See, level of accuracy means that here when we are using a colorless solution, we are simply adding universal indicator to it, and that solution is getting some color, and then it's very clear to us that we have to just match that color with the pH value. Okay, but when the solution is already colored one and then we are adding universal indicator to it, so what is happening? So already colored solution and then adding universal indicator makes what is happening is the universal indicator is like bringing out some color change, okay, in the solution, and the solution already it has some color. So because of this, the colors, we may not get exact color, okay, the correct color, okay, and if we are not getting the correct color, then we may not get the correct pH value. Because of this mixing of colors, we may not get the correct color, okay, and because of not getting the correct color, we may not get the exact correct pH value, okay. So that's why I have said that when we are using colored solution, okay, at that time, and where we are using universal indicator to find the pH of that colored solution, the level of accuracy is not very much high. Okay, now moving ahead, let's now see the acid-base indicators. We have seen how we can use pH paper, how we can use universal indicator to find the pH. Now we will see how we can use acid-base indicators to know whether the particular solution is acidic, basic or neutral. So first acid-base indicator we are going to learn is litmus solution and litmus paper. Now we call this litmus solution and litmus paper as natural indicators. Now why is this so? Because we obtain them from lichens. Okay, and this lichens, okay, you can see in this image, not the wood, but on that wood you can see this gray flower like structures, okay, means like leaf like structures. So these are lichens. These are actually the organisms, okay, from which we obtain this litmus solution. Okay, that's why since we are obtaining it from natural sources, we call this indicator as natural indicator. Okay, now litmus solution is of two types. You can see here red litmus solution, blue litmus solution. Similarly, litmus paper is also of two types, red litmus paper and blue litmus paper. Now how you would make litmus paper? We know litmus solution is made from lichens. So litmus paper is simply what we have to do is just take a paper. Okay, litmus paper, how it is made? A paper is dipped in the red litmus solution and that paper becomes red litmus paper. When a paper is dipped into the blue litmus solution, that paper becomes blue litmus paper. Very clear, very simple. Now how we can know whether the particular solution is acidic or basic or neutral, okay, with the help of this litmus solution. So I will simply tell you a trick. The trick is in front of you. I have drawn the beakers, okay, and I have drawn the colors of the solution. So you have to simply remember that if the particular solution is acidic, okay, if it is acidic, whether you pour red litmus solution or you pour blue litmus solution, the color would change to red. Red, acid, danger, right? You can remember in this way. Or if the solution is basic, okay, whether the litmus solution you are pouring is red litmus solution or blue litmus solution, in that colorless solution, okay, we are talking about the colorless solutions, colorless acidic solutions, colorless basic solutions. So whether you are pouring red litmus solution or blue litmus solution into this colorless basic solutions, what would happen? The color would become blue. Okay, the color would be blue of that solution. Okay, so with this simplest trick, you can easily remember how the color of that litmus solution changes, and if it is changing to a particular color, then that particular solution is acidic or basic. Okay, so suppose now I'm asking you, okay, don't look at this, okay, I'm just standing here. So if I'm adding, okay, in a colorless solution, red litmus solution, okay, and if that solution is acidic, so what would happen? The thing should click in your mind. Whatever be the litmus solution, the color would be red, right? So what had happened? I have added red litmus solution to the acidic solution and color remained red. So you can just easily interpret it, right? I have just shown you an example. If suppose we are having a basic solution, okay, now I am telling you to add the red litmus solution into it. So what would be your, what is the trick to remember? If it is a basic solution, color would become blue. Okay, whatever you add, whether you add red litmus solution or blue litmus solution, so color would become blue. So what you would say, in basic solution, red litmus solution's color would become blue, right? See, in this way you have to remember. Very simple. Okay, so far we have seen about the acidic and basic. Now you just think on your own that what would happen to the red litmus solution and blue litmus solution when we would pour it in the neutral solutions. Okay, so think for a while. So suppose if you would have guessed, what happens with the neutral solution? The red litmus solution, okay, when we are pouring into a colorless neutral solution, the color becomes red. Okay, and when we are pouring blue litmus solution in the colorless neutral solutions, okay, the color becomes blue. There is no change in the color. Okay, no change in the color, right? In case of neutral solutions. Okay, very clear. Now the same logic is applied to the litmus paper. Exactly the same. See what we have learned, the acidic solutions color would be red, right? So when we are dipping our red litmus paper in acidic solutions, it would remain red, right? But when we are dipping blue litmus paper in acidic solution, color should be red only. So that blue litmus paper's color would become red. The portion which we have dipped into the acidic solution, it would become red. Same with the base, color should be blue, right? So when we are dipping red litmus paper in the basic solution, the red litmus paper would become blue, okay, whichever part is dipped. And when we are dipping blue litmus solution in the basic solution, color should be blue, so it would remain blue. Okay, the color won't change. So this is the simple logic which you can use. Okay, and in neutral solutions we already have seen there is no change in the color. Okay, so red litmus remains red, blue litmus remains blue. Okay, no change in the color. So was it easy? Okay, now let's quickly test whether we have understood the litmus solution concept or not. Okay, so if in a solution red litmus solution is added, I'm having a solution, colorless solution, red litmus solution is added. Now I am adding this red litmus solution into it. What they have given is there is no color change. No color change means this red litmus solution here, after adding it into this colorless solution, okay, it would remain red only. Okay, no color change. So what is the nature of this solution? Okay, now we know when the color is red, this means that the solution is acidic, first of all, right? So yes, acidic, it can be acidic. But we also know that in neutral solutions also, the color of the litmus solution doesn't change. Okay, it remains as it is. If we are adding red litmus, the color would remain red. If we are adding blue litmus, the color would remain blue. So this solution can also be neutral, right? Now the question arises, how to figure out that this solution is whether acidic, okay, or whether it is neutral. Okay, now we have a simple trick to it. What we can do, we have tried with the red litmus now. Now we would add blue litmus. Okay, now if after adding blue litmus in our colorless solution, if that blue litmus would turn red, okay, so then we can say that, oh, this has turned red. Now this solution is acidic, right? So then we can say that, yes, definitely this solution is acidic, okay, out of acidic and neutral. But if our blue litmus solution remains blue, okay, after adding, if our blue litmus solution after adding into the solution, the color of the solution remains blue, So then we can say that, oh, see, after adding red, it was remaining red. After adding blue, it was remaining blue. Then that means the solution is neutral. Okay, so was it interesting? Now, our next acid-base indicator is phenolphthalein. Okay, so phenolphthalein indicator solution, it is colorless. Okay, now I'm calling it a solution, right? Because we are making this phenolphthalein indicator solution by dissolving, by using water. Okay, very simple. Now this colorless solution we use in order to identify whether the solution is acidic, basic or neutral. So how we can use it? See, we are having this colorless, acidic, basic and neutral solutions. Okay, now I'm having colorless phenolphthalein solution. So I'm going to add I'm going to add it in the colorless acidic solution. So what would happen? There would be no change in the color. This colorless acidic solution will remain colorless only. So this means that our phenolphthalein remains colorless in acidic solution. Okay, there is no change in the color. But when I add our phenolphthalein in basic solution, okay, which is colorless, now what happens? The color of the solution becomes pink. Okay, wow. So what we can say is our phenolphthalein, which is colorless, in basic solution, it changes to pink, right? Very simple, the same logic which I have told you. Remember the color of the solution, that's it. Then you can easily tell that the indicator's color is changing from which color to what color. Okay, here the color of the solution in basic solutions, in case of basic solution, since we are taking a colorless basic solution, after adding phenolphthalein, the color of the solution becomes pink. So this means our phenolphthalein from colorless, it is changing to pink, right? That's why the color of the solution is getting pink. Simple. And in the neutral solution, it's very simple again. The colorless neutral solution remains colorless. Okay, after adding phenolphthalein in it, no change in color. So our solution remains colorless. That's it. So that this means that our phenolphthalein also remains colorless, right? Very simple. Now moving ahead to the methyl orange indicator solution. Okay, now its name suggests, and it's very easy to remember, from its name only we can remember that this methyl orange indicator solution has orange color. Okay, now we will also use this indicator in order to find out the solution is acidic, basic or neutral. Okay, so what happens when we add methyl orange indicator in acidic solutions, basic solution and neutral solutions? Now we are here talking about the colorless acidic, basic and neutral solutions. Okay, now first is acidic solution. Now it shows slightly different colors. Okay, so when we add methyl orange into acidic solution, which is colorless, what happens is the color of the solution becomes red. Okay, so this means that we can now say that our methyl orange indicator, which is orange in color, right, it is turning to red, right, in acidic solutions. Correct. Now when we add our methyl orange indicator in basic solution, okay, which is colorless, so what happens? Let's see. The basic solution becomes yellow. Okay, so this means that our methyl orange indicator, which has orange color, in basic solutions, its color changes to yellow. Okay, very simple. And lastly, in case of neutral solutions, again, when we add methyl orange into the colorless neutral solution, the color of the solution becomes orange. Okay, so this means that if it is orange, so see, the color of the solution becomes orange. This means that the orange color of our methyl indicator remains orange. Okay, so no change in the color of methyl indicator. Very simple. Now I will tell you a trick to remember this. In case of phenolphthalein, what you only remember is simply, you remember that in basic solutions, phenolphthalein, when we add phenolphthalein, the color of the solution becomes pink. That's it. In acidic and neutral, then it would be automatically fixed in your brain that there is no change in the color. Okay, then you can clearly tell that, okay, see, if in basic solutions the phenolphthalein, when I'm adding, the colorless solution becomes pink, this means that our colorless phenolphthalein is changing into pink color. Very simple. And in case of methyl orange, okay, since there are two colors, from orange it is changing to red in acid. Okay, when we are adding into acid. So you can correlate this with the litmus solutions. In litmus solution also, right, the acidic solutions would be red okay, whether you add red litmus or whether you add blue litmus. So same case in the acidic solutions, okay, if you add methyl orange indicator, it becomes red. So then you could easily remember that our orange color methyl orange indicator is changing to red in acid, okay, red, danger. And in case of base, so see, in case of acid, it is changing to a darker color from orange to red. Then it's simple to remember in case of base, it is changing to a lighter color, orange to yellow, right? So simple trick. And lastly, in case of neutral solutions, okay, as the same like phenolphthalein, it also doesn't show any change in the color. So methyl orange indicator, its orange color also doesn't change. So that means that our neutral solution, okay, when we add methyl orange into it, it would become orange. Okay. Now moving ahead to the last type of indicators, and this is the last topic of this chapter, and which is olfactory indicators. Okay. Now this is quite an interesting type of indicator because they are doing something different. Okay. What they are doing, these are the substances which are showing change in their smell in acidic or basic solutions. Okay. Now, for example, we can see onion, clove oil, vanilla, these all are olfactory indicators. Now let's see an example in detail about onion. Okay. So if I'm having a cloth piece, okay, I would tear it up and what I would do, I would apply onion extract on that both these cloth pieces. Okay. It's very simple. Now what I would do, I would just dip, okay, one of the cloth piece in basic solution and another cloth piece in acidic solution. Okay, suppose I'm having two solutions. One is acidic, one is basic. I know. But which one is acidic, which one is basic, I don't know. So how can I quickly make out that which one is acidic and which one is basic? I would just tear the cloth of cloth strip, apply onion extract, dip one cloth strip in basic, dip one cloth strip in one solution, dip another cloth strip in another solution. Now, when I would find that after taking out the cloth strips, the cloth strip whose smell is vanished, okay, smell is vanished, that cloth strip which was dipped in the solution, that solution is basic solution, okay, and whose smell is not vanished, it is acidic solution, okay. Now, how to remember this thing? It's quite confusing, I guess. So, in slang Hindi, smell is called as baas, okay. So, the baas of onion, okay, it just vanishes in base, baas, base. Very easy, okay. So opposite would be for the acid, the baas would not vanish in acid, right? Now it's time to see some questions, but I would suggest you that after seeing the question, you just pause it, try to solve it on your own, and then unpause it to see that whether you have just found the correct answer or not, okay. And before solving the questions, just go through the notes which you have prepared so far till this video, okay, because that would help you. If you would revise it, you could solve the questions in a better way, okay. So now first question is, the pH of acetic acid, okay, is greater than the dilute sulfuric acid, okay. Here this is the dilute sulfuric acid, H2SO4, this is acetic acid, CH3COOH. No need to, no use of this formulas here, but just to make you aware. Now what they are asking, so the acetic acid contains dash concentration of H plus ions, okay, greater, same, low, okay. Now you have to use the pH concept here, okay. So what I would do is, see, the pH of acetic acid is greater, they are saying me. So suppose I am taking a random number, okay. Now since they are acids, their pH won't go out of that 7 line, okay. So suppose if the pH of acetic acid is greater than dilute sulfuric acid, I am taking that acetic acid's pH is like 6, okay, or like 5, and dilute sulfuric acids, okay, I am just representing it in this way, S, okay, dilute sulfuric acid, its pH would be less, na? See here, pH of acetic acid is greater than dilute sulfuric acid, so it is 5. pH of acetic acid is 5, it is greater than the dilute sulfuric acid, so it should be less than 5. So suppose it is 4. Now they are asking us that, so acetic acid contains dash concentration of H plus ions, greater, same, or low. Okay, so we can use this pH value and try to find their hydrogen ion concentrations, okay, with the help of simple formula. We know hydrogen ion concentration is equals to 10 raised to minus pH, right? So for acetic acid, it would be 10 raised to minus 5, okay, this would be the hydrogen ion concentration. And for sulfuric acid, what would be the hydrogen ion concentration? Okay, its pH is 4, so 10 raised to minus 4, correct, minus pH, 10 raised to minus pH, so 10 raised to minus, I'm just putting the value, 10 raised to minus 4. Now you can clearly make out, okay, there would be no confusion. See, 10 raised to minus 4, 10 raised to minus 5. Now you already know this, 10 raised to minus 5 is 0.00001, right? 1, 2, 3, 4, 5. And this 10 raised to minus 4 is 0.0001, right? So 1, 2, 3, 4. So which one is the smaller number? We know this is the smaller number, right? So H plus ion concentration is smaller of acetic acid as compared to sulfuric acid. So see, so acetic acid contains low concentration of H plus ions, right? Very simple. Yes, we have got this from the formula. Okay, we have solved this. Very simple problem. Now, the indicator which does not change color, okay, does not change color on passage of HCl gas is dash. Okay, now here you need to just apply the concept of this HCl gas. When it is getting dissolved in water, it would form HCl solution. Okay, so this you should know. It's like quite tricky one. Okay, but now once you know this, the HCl gas should dissolve in water, then it would become HCl solution. Now we know HCl solution is acidic, right? Very simple. So when the methyl orange indicator is there in our beaker, okay, we know that this methyl orange indicator solution, it has water, right? So when we would pass HCl gas, so that HCl gas would dissolve in water, it would form HCl solution, and HCl solution is acidic. So what would happen? The acidic solution is getting formed in methyl orange, and we know methyl orange, when we add it in acidic solution, what happens? The orange color becomes red, danger, right? So orange color would become red, so it would change the color, right? This is changing the color. Methyl orange would change the color. So this would not be our answer, because they are asking which does not change the color. Okay, next is moist blue litmus. Okay, now we know that this blue litmus, okay, now moist one. So moist means it has some water. So when we would pass the HCl gas, the HCl gas would dissolve in that water, it would form HCl solution. HCl solution is, again, we know it is acidic. So when acidic solution would form on this litmus paper, which is blue. Now we know acid means red. Yes, we have kept it in the mind. So on blue litmus solution, the acid would, like, because of this acid, this blue litmus solution would become red, because acid means red, right? So blue litmus turns red. We have remembered in this way. So this would also change the color then. Okay, so this is also not the right answer. So what would be remaining? Phenolphthalein. So phenolphthalein is our right answer. Okay, so we know now this is remaining, so this would be our answer. But let's just see why. See, phenolphthalein, we know that in acidic solutions, when we add phenolphthalein, it doesn't show any color change. Phenolphthalein solution is colorless. In acidic solution, it also remains colorless, right? So when in phenolphthalein, the HCl gas is passed, it would form HCl solution, just like the same it formed in methyl orange solution indicator. It would form HCl solution here also. But this HCl solution, we know it is acidic, and phenolphthalein does not show any change in the color in acidic solution. So no color change would be there. So see, does not change color. Yes, this is not changing the color. So our right answer is phenolphthalein. Okay. Now moving to the next question. Write a balanced chemical equation for each of the following reactions. Okay. So first reaction is action of dilute sulfuric acid H2SO4 dilute one on zinc sulfide. Okay, on zinc sulfide. Now you can try on your own. If you would have studied it, if you would have understood the concept, okay, of action of dilute acid on metallic sulfides. Okay, you remember what is going to be formed? Yes, the metallic salts and hydrogen sulfide gas. Okay, so hydrogen sulfide gas is going to be formed, metallic salt is going to be formed. Now see, hydrogen sulfide gas, apart from hydrogen sulfide gas, which salt would be formed? How would we make out? See, this hydrogen, okay, and this sulfur, okay, these are used for formation of H2S. Now what is remaining? SO4 and Zn. and what would be formed? ZnSO4, zinc sulfate, right? Zn2 plus SO4, 2 minus, it's getting balanced. So ZnSO4 would be formed. Now balance the reaction, zinc, zinc, 1, 1, sulfur. Here there are 2 sulfur atoms. Okay, here there are also 2 sulfur atoms. Again moving to hydrogen, 2 hydrogen atoms, 2 hydrogen atoms. Then sulfur we have balanced, and oxygen 4. Okay, so here also there are 4 oxygen atoms. So it's balanced. Now previous 2 questions were asked in your examinations in 2020. This question is asked in your examinations in 2019. Okay, so see what we have learned, we can apply it and then we can solve the questions as well. Okay, very comfortably, very easily. Okay, next is action of dilute hydrochloric acid on magnesium sulfide. You try it on your own, then unpause it to see the answer. So we know magnesium sulfide, MgSO3. Okay, now this is a metallic sulfide. We know when dilute acids act on metallic sulfides, what do they give us? They give us salt, okay, water and sulfide. So SO2 gas is released. Okay, so I would write the reaction then. They are asking me the reaction. So I have just written what is the general reaction. I remembered it and I tried to write the reaction. First the simple things. Now dilute hydrochloric acid is given to us. So I am writing here dilute HCl. Okay. Now I want to make this the salt and it's done. After that I would just balance the reaction. So salt would be, see, H2O, SO2. So hydrogen and oxygen and sulfur are involved. Okay, so hydrogen, oxygen, sulfur are involved. What is remaining? MgNCl. So MgNCl would form MgCl2. We know magnesium chloride. Now balance it. Oh, magnesium 1, 1, chlorine it's 2, 2 here. Okay, hydrogen 2, hydrogen 2. Okay, then there are no hydrogens here. So magnesium is done. Okay, chlorine done, hydrogen done. Now remaining is sulfur and oxygen. So sulfur is 1 here. On that side also sulfur is 1, oxygen 3. Okay, so oxygen 1, 2, 3. Okay, clear? Next is state one observation for each of the following. First is A. We have to state one observation. Okay, so I have told this type of question to you when we were learning. So what is the question? A small piece of zinc is added to the dilute hydrochloric acid. So first what we would do, we would just write the reaction. Okay, zinc is added to dilute hydrochloric acid. Now can we figure out from here only? See, zinc, metal added to the dilute acids. So when dilute acid react with metal, we know what would be formed? Metallic salts and hydrogen gas. So no need to write the entire equation as well. We know hydrogen gas is going to be formed. So observation, we would write the gas which is going to be formed, but not the gas. We are going to write the test for that gas. So we know for the hydrogen gas, the test is very simple. The gas evolved extinguishes burning splint. Right? We have learnt it. And itself burns with pop sound. Okay. Now next is, so this was asked in a 2019 examination. Okay, next is action of dilute hydrochloric acid on iron 2 sulfide. So iron 2 sulfide here means our Fe is in +2 state. Okay, so Fe is in +2 state. Sulfide, we know S means sulfide is the salt which is having S2 minus ion, right? Sulfide ion. So Fe2 plus S2 minus, it would form FeS. Okay, action of dilute hydrochloric acid. So dilute HCl. Okay, on iron 2 sulfide. See, dilute acids on metallic sulfides. Just now we have seen what they give us. Metallic salts and hydrogen sulfide gas. Okay, is released. So observation would be that hydrogen sulfide gas is released, but we won't write that this hydrogen sulfide gas is released. We would write a test for this gas. So what is the test? A gas with rotten egg smell is released. Correct? Because we know hydrogen sulfide gas is having rotten egg like smell. Okay, so gas with rotten egg like smell is released. Next one is name the gas that is produced. Name the gas that is produced when dilute hydrochloric acid, okay, reacts with sodium sulfide. Okay, asked in 2018. So now you would have agreed. See, sodium sulfide is this. Okay, sodium sulfide. So the gas that is produced when dilute hydrochloric acid reacts with sodium sulfide. Okay, so again metallic sulfide reacts with dilute acid, it forms metallic salt and H2S gas, right? We know this. We remember the general equation. So H2S gas is getting released. So answer is H2S, hydrogen sulfide. Okay, very simple. So that's why I was telling you that like this topic, the action of dilute acids on the salt is like the favorite for the for the people who set your examination paper. Okay, so please don't ever let this topic go. Okay, you would lose marks. Now next is potassium sulfide. Let's write the formula K2SO3. So always have that habit of writing the formulas because it would make your work easier. Okay, so potassium sulfide K2SO3 on reacting with hydrochloric acid. Okay, when this is reacting with hydrochloric acid, it releases dash gas. Okay, now we know, see, SO3 sulfite, metallic sulfide, right? So metallic sulfide reacts with dilute acids or acids. Okay, and they give us what? They give us salt, water and SO2 gas, right? So they are just asking us the name of the gas. It releases dash gas. So our answer is SO2 gas. Okay, out of the Cl2, SO2 and H2S, SO2 gas. This was asked in your examination in 2017. Now moving on to the next question. The pH values of three solutions A, B and C are given in the table. Okay, answer the following questions. So A is having pH value 12, B is having 2, C is having 7. So what are the questions? Which solution will have no effect on litmus solution? Okay, so see, litmus solution, no effect on litmus solution. So they are asking about both red litmus solution as well as blue litmus solution. Okay, so don't get in a hurry, okay, or don't get confused. See, so which solution would have no effect, okay, on red litmus as well as blue litmus? So we have just studied neutral solutions, right? In a neutral solution, okay, whether you add red litmus or whether you add blue litmus, the color would be the same as that of the litmus solution. No effect. Okay, no effect. If in case of acids and bases, we know that in case of acids, the red litmus remains red, but blue litmus becomes red. Okay, in case of bases, the red litmus, it becomes blue, but the blue litmus remains the blue. Okay, in basic solutions. But neutral solutions, red litmus remain red, blue litmus remain blue, right? Because whatever the color of the litmus solution is there, that color is taken up by the neutral solution. Okay, so no effect would be shown by the neutral solution. Now, which of these three solutions is neutral? Okay, they have given us the pH value. Now we have studied this, the concept 7 pH value is there, then the solution is neutral. Okay, so which solution? Our answer would be C. So first answer is C. Okay, then which solution will liberate carbon dioxide, okay, when reacted with sodium carbonate? Okay, so sodium carbonate, I would write it here, Na2CO3. Okay, the particular solution that would release carbon dioxide. So can you try to correlate this reaction? See, carbonates, when they are reacting with a particular solution, they are releasing carbon dioxide. Have something clicked in your mind? Dilute acids, right? Dilute acids react with carbonates and they produce salt, water and carbon dioxide. So this should be a dilute acid. Now dilute acid, out of this two, which would be the acid? Okay, dilute, leave about the dilute. Okay, which would be the acid? So out of A and B, our pH value, having 2 pH value, would be acid, right? Because below 7 the solution is acidic, right? So our answer would be B of second. Okay, and C, which solution will turn red litmus solution blue? Okay, so we know it would be A, but see how A? See, red litmus solution is getting turned into blue. Now when you just see blue, you should remain basic solutions. Okay, basic solutions would turn any litmus solution blue. Okay, basic solutions would have blue color. Colorless basic solution would have blue color. So that means it turns red litmus also blue, blue litmus also blue, right? So here it turns red litmus also blue. See, red litmus also blue, red litmus solution blue. Which? Basic, right? So now basic solutions are the solutions which are having pH more than 7, right? So here pH value is 12. It's matching. Okay, so our answer is A of third. And this question is asked in your examinations in 2019. So whatever questions we are solving, they have been asked in your examinations from either starting from 2020 to 2017. Okay. Now the last two questions, three solutions P, Q and R have pH value 3.5. This means P is having pH value 3.5, Q is having pH value 5.2, R is having pH value 12.2. Okay, respectively. Okay, this respectively means this thing. Which one of these is a first weak acid? Okay, now you can clearly make out. See, 3.5, 5.2, 12.2. Now here, below 7, the solution would be acidic, right? So 12.2 will not be our answer. Now out of these two, 3.5 and 5.2, we have to find weak acid. Okay, so that particular weak acid, okay, if it is weak, okay, weakly acidic in nature, this means that it should be close to 7, right? Close to 7. If it is farther from the 7, okay, then we know that when we move farther from the 7, acidic nature increases. Okay, now opposite would be when we would move close to the 7, acidic nature decreases. So the value which is closest to the 7, its acidic nature would be the least. Now out of this, which value is closest to the 7? 5.2. So its acidic nature would be lesser than the 3.5, right? You have to just apply the concept, okay, which we have learned so far. So which it is? Q. Okay. Now second is strong alkali. Now no doubt 3.5, 5.2 cannot be our alkalis, and they are asking a strong alkali. So see, 12.2, it is like way away from 7. Okay, it is very much closer to 14, and we know when we move away from 7, okay, our alkaline nature, it increases. Okay, so here when we would reach out to for 12 or something, the alkaline nature would be so high, so it would be a strong alkali, right? So our answer would be 12.2 is R. Okay, very simple. Now the last question, choose the correct answer from the options given below. Okay, so this was asked in 2017. To increase the pH value of a neutral solution, okay, so they have given us neutral solution. This means that solution is having pH 7, and they are asking us to increase the pH value of this neutral solution. Okay, what they are asking us, what we should add. Okay, an acid salt, an alkali, or a salt. Okay, so let's see. So in order to increase the pH value of neutral solution, which means we are going to make it 8, 9 or 10. Increasing the pH value of neutral solution means increasing the value from 7. Okay, because neutral solution is having pH value 7. So increasing the value above 7. Okay, 8, we can make it 8 or 9 or 10. Okay, this means the increase in the pH value of neutral solution. Okay, so what we are actually doing is we are making the solution alkaline, right? Now just think for a while. We have studied the story. Now in that story I have told you, when we are adding acid, what is happening? Hydronium ions concentration increases, right? But hydroxyl ions concentration decreases. Because of that, what happens? Hydronium ions concentration is more than hydroxyl ions concentration, correct? Okay, now, okay, how hydronium ions concentration is increasing, hydroxyl ions concentration is decreasing. Okay, because of that, what is happening? Hydronium ions concentration is becoming more than the hydroxyl ions concentration. So this solution becomes acidic. We know acidic solutions have this hydronium ions concentration more than hydroxyl ions concentration. We want alkaline solution, right? So this is wrong. In case of an acid salt, we have learned the acid salt. Try to remember, an acid salt has an ionizable hydrogen atom, right? And I have given you a reaction in which I have explained you how that ionizable hydrogen atom gets ionized and forms H3O plus ions, right? Hydronium ions. So same it would be like acid only. It is also producing hydronium ions. So hydronium ion concentration would increase. Because of that, means hydronium ion concentration would increase. And we know that hydroxyl ions concentration decreases. Okay, why you would study in higher classes, but hydroxyl ions concentration decreases, right? So what would happen? The same case would happen. Hydronium ion concentration would be greater than the hydroxyl ion and it would become acidic. So we want to make it alkaline. So we cannot use an acid salt. Now moving to an alkali. Okay. See, when we are adding alkali, we know that hydroxyl ions concentration increases, right? And hydroxyl ions concentration increases. At the same time, hydronium ions concentration decreases. Okay. But because of this, what is happening? Hydronium ions concentration is becoming lesser than hydroxyl ions concentration, and this such solution is, like we know, alkaline solution or basic solution. So yes, by adding an alkali we can make the solution alkaline. So our right answer is an alkali. Okay, so why no need to worry about this last option, a salt? Because we have just only studied the salt which is made up of strong acid and strong base, right? And that too, that salt, when we added in the water, the solution remained neutral. Okay, so does it make the solution new alkaline? No. Okay, so this cannot be our right answer. So our right answer is just, that's why I told that our right answer is an alkali. Okay, so friends, with this we have reached the end of this video and we have completed this chapter as well. We have studied all the concepts of this chapter: acid, bases and salts. Okay, so I hope you would have enjoyed learning with me. You would have understood all the concepts, but please do let me know this thing in the comment section. And as you all know, LearnHub matlab free hai par best hai. So see you in the next video with the next chapter. Till then, stay tuned. Take care. Bye bye and have a great day.